So last time we were seeing in the previous part how the linking number changes if we change the orientation of some parts. So I was mentioning this in the end, but I'll just repeat it because it got a little bit unclear towards the end. That if you want to forget about orientation, like you want the linking number to be an absolute value of the link, really not depending on orientation, because orientation is like an artificial external sort of thing, is not really part of the knot. You want it to be like separate from orientation. We see that the absolute value of the linking number is the same no matter if we change how much ever times we change this. The absolute value is the same. So if we take absolute value of linking number mn, this is independent of orientation. Though to arrive at the value you have to orient, calculate, and then take absolute value. So to arrive at the number you have to put orientations, but the value itself is independent of orientations, if you see what I mean. So this is just, generally whenever we say linking number, we actually mean absolute value of linking number. So now let's prove that linking number is invariant under ambient isotopy. As in, given two links, you use Reidemeister moves and wiggle them around. Is it true that linking number remains the same? Because I told you in the beginning about invariance, how invariance should remain the same as you wiggle them around. Let's prove that for linking number. The proof will be a bit messy and involving a lot of cases, but I'll show you. I won't show all the cases. Like for Reidemeister moves, I didn't show you all the cases for every single possible Reidemeister move. Like that, I'll show you the idea, so that if you want to, you could write out all the cases. But I'll just show you the basic idea of the proof. So, there are three Reidemeister moves you have to check. We have to check for Reidemeister 1, Reidemeister 2, Reidemeister 3. Because if for each of these three, linking number is remained the same by applying each of these moves. That means that for all possible motions, linking number remains the same, because by Reidemeister's theorem, any motion can be decomposed into these moves. So we only have to check the Reidemeister moves. Now, we can actually not even do Reidemeister 1. Let me tell you why Reidemeister 1 is automatically done. The crossing in a Reidemeister 1 is always an internal crossing, because if you just have one strand, this crossing, if you call this component M, this strand is M, this strand is also M. So this crossing is an internal crossing. In definition of linking number, we said to only consider the crossings which are between the different components. This crossing is in the same component, so this can be completely ignored. So Reidemeister 1 is already taken care, because it's not even coming into the linking number calculation. So the two real things we have to check are Reidemeister 2 and Reidemeister 3. So let's look at Reidemeister 2 first. So I will only consider one case here. So obviously we want our two strands to be of different components, because like before, if this was M component, this was also M component, doing any weird thing in between them, all crossings will be internal crossings of M, so we will ignore them in linking number calculation. So we only really need to consider the case of M and N, and I will also consider the case where they are in the same direction. I will also just consider the case where they're both in the same direction. You will also have to consider the case where it's in the below direction, and that's why I said I'm skipping some of the cases, just for showing the idea. So let's see. In a Reidemeister, so as of now, the linking number of this portion is 0, because there are no components. The outside portions have a lot of other linking numbers, but just this portion has a linking number of 0. Now, if I shove this part underneath, you also have to check the over case, where you shove it over. We'll just check that. For simplicity, I'll just check the underneath case. So the orientation is like this. So in this case over here, what we have on this crossing is this one and this one. So we go like this and like that. Thumb is pointing inside, it's a -1 crossing. You can also think like this. To rotate from here to here, We are going in a clockwise direction. And therefore there's a -1 crossing. So this crossing here is -1. Now let's check the upper crossing. We go like this and we go like that. It's an out crossing. Similarly, if you want to think, you go like this, like that. Rotation is counterclockwise. That's a +1 crossing. But the basic idea is that overall, the net change is 0. So it's still 0. It's +1 -1. So after we also have 0. Means the change, so I'll write that as delta L. Delta generally means change, and L is a linking number. So delta L is 0, which is exactly what we want. We want there to be no change in the linking number. Now the only thing left to check is the Reidemeister 3 move. Now this one especially has a lot of cases. I will just show one case. You can check all the other cases on your own. So let's see. So I will consider the case where I'm gonna orient these like this. And I'm gonna consider just assume that these directions are like this. And I'll also just, for simplicity, assume that these are both from the M component. I'm making a lot of assumptions here. There are many other cases you have to check, like 16 cases or something. You will have to check on your own. I will just show you one case. Let me just read out this diagram. So assuming this is an N component. So the side of this crossing is 0 because it's an MM. What is M? Z. It's an internal crossing, so the sign is 0 as of now. Sign here is 0 of this crossing. Okay. Now this crossing, let's talk. Orient your hand like this, orient your hand like that. Thumb points outward, this is a +1 crossing. And you can check that it's a counterclockwise rotation to get from over to under. This is a +1. Similarly here, what we have is we have to rotate the overstrand to the understrand. And the understrand orientation is in this direction. So like that, we have to rotate. That's a -1 crossing. So the total linking number as of now is 0. Now if we move the strand over to the other side, I will not show the calculations. You can do this on your own. When you move it to the other side and keep the same orientations, you can go to the calculations again. Check each crossing. There's 2 crossings you have to check. They will both turn out to cancel out and be 0. This is just a very computationally intense proof. You can do that on your own and find that even for Reidemeister 3, delta L is 0. Thus, if all the Reidemeister moves preserve linking number, then by Reidemeister's theorem, any motion from one knot to the other will have to preserve linking number. Thus, linking number is a knot invariant. Now, in the next part, we will first do some examples of linking number and show some interesting results, and then we will consider another knot invariant called tricolorability. We will see that in the next part.